Scientists have confirmed liquid water flowing on the surface of present-day Mars. That's the news that made headlines in 2015. Using an imaging spectrometer, researchers detected hydrated minerals where mysterious streaks are seen on the red planet. Mars researcher Dr. Raymond Arvidson at Washington University breaks down this new information and his involvement.
I got the front page of USA Today, and the quote was, water is the elixir of life. And that was a quote from me, and then throughout it's the article proper.
That's because Washington University's Dr. Raymond Arvidson is one of the leading researchers evaluating the evidence, presenting the findings to the world. The Mars Reconnaissance Orbiter provides evidence of flowing liquid water playing a vital role in the formation of the dark, narrow streaks on the slopes at Hale Crater. The streaks darken and appear to flow down steep slopes during warm seasons and then fade in cooler seasons. They appear when temperatures are above minus 10 degrees Fahrenheit and disappear at colder times. Using an imaging spectrometer, researchers detected liquid water. But it's not the liquid water we think of here on Earth. Dr. Arvidson says this is hydrated salt, or brine. Brine is a form of water concentrated with salt.
Brine is what forms, when we put salts on the roads when they're icy and snowy. You wouldn't drink it, right? And the brines that likely powered these dark streaks on Mars were even brinier. And if you have a lot of salt, it becomes more of an oil-like fluid than water. So we still have a lot to understand in terms of, what concentration of brine are we talking about? Where does it come from? How does it go from an ice with the salt in it to a brine that powers these sediment streaks that go downhill?
This is a look at what Mars is believed to have been like billions of years ago, warm enough to sustain oceans of liquid water, lakes, and flowing rivers, critical for life. Present-day Mars is below freezing, cold and dry. There is ice at the poles and some water vapor, but the discovery of a flow of briny liquid water is giving scientists new focus.
There's a very nice camera in orbit aboard the Mars Reconnaissance Orbiter. It's called HiRISE. So you can see things as small as about a yard across. And they keep looking at cliffs. And when the sun hits those slopes, for whatever reason, this chlorine-rich salt goes from an ice to a liquid and apparently causes this sand or debris of whatever kind to move downhill. So it's really interesting. We're trying to figure out whether it's coming from the subsurface or from ice that's been left on the surface from some relatively recent event. There's a modern hydrologic or water cycle on Mars, but it's mainly vapor and ice. But now we can add to it brines.
Arvidson wears many hats with NASA and many titles, making him one of the country's leading Mars experts, and he's very much involved in the processing of the latest discovery. Arvidson is part of the CRISM team. CRISM stands for the Compact Reconnaissance Imaging Spectrometer for Mars.
CRISM is an imaging system, but it takes pictures in many, many different wavelengths. And there are wavelengths that you can look at from the visible through what's called the infrared, and it allows you to pick out diagnostic information, spectral information for the presence of these salts, these what are called perchlorate salts. So they're chlorine mixed with oxygen, but water in the lattice. And it's pretty complicated, but what it means is that there's an ice that's able to be melted at temperatures very much lower than pure water.
And Arvidson will continue to play a role advancing the research. Higher resolution images could soon be achieved thanks to the work of one of his senior students working in his lab last year. Before graduating from Washington University, Christina Kreisch developed an algorithm reducing the noise in the CRISM data and imaging.
The idea of this is that the spectrometer is taking these image cubes, which contains not only spatial information about what the scene looks like, but more importantly, mineralogical information. And so with our algorithm, we're wanting to basically remove the noise from the spectra we're getting from those image cubes.
The CRISM team is advancing Christina's work to better understand the discovery of brine.
What's been published, and it was in Nature Geosciences, was based on one single spot. And with Christina's code that's been changed and augmented since then, but she's been involved, we can see all the spots. So we can map out the whole dark feature all the way back up to the cliff. So we'll be able to do much more now that we can get these really very nicely oversampled data and use the code to generate images and spectra with much finer resolution than you could before. In fact, we requested with the CRISM team to get a lot of these super resolution image collections, hyperspectral image collections, over those same spots. And what we're doing now is going back and reconstructing all the dark areas, with the special regularization or processing that we developed.
Which is the first step that could one day lead to bigger ones.
So we need to understand how these things form. And that leads to whether or not we can eventually send either humans or robotic systems to explore them. Now, there's a kind of a bug here in that if we find that these areas are recently wet, which seems to be the case, they're called special regions. And special regions defined by NASA are regions you have to be really careful because they might contain extant life. So you don't want to go to them with any old robot spacecraft. It has to be super clean to make sure we're not putting microbes into this fluid, which could then kind of propagate, through other areas of Mars. They're called special regions. So if we continue to confirm that these places have brines, not pure water, but brines, we have to be incredibly careful about how we explore them.
After all,
water is the elixir of life, even briny water.
And everyone knows what that could mean: life on Mars.
We're not going to meet the green people or the invaders from Mars. If at best, these probably would be very low-level life forms, the equivalents of microbes on the Earth.
So to do it right, Arvidson says a close-up and more personal investigation could be another 20 years from now. That's using machines. Even longer for a human expedition.
Trying to do through what's called the Mars Exploration Program Analysis Group, or MEPAG, that I used to chair, but no longer. They're developing, what are the requirements for a mission to a special region? What degree of cleanliness, what can they do and not do in order not to forward contaminate Mars?
Right now, there is no special rover planned for the investigation. Arvidson says it's too soon. More evidence and planning is needed.
Is that the best place? Are there other areas, where these streaks are forming more commonly and they have a much more extensive salt signature? There's a lot of work to do to understand the dynamics of these systems, the extent to which, how much brine was involved, the habitability, the feasibility of landing on a slope or driving or landing on a flat area and driving to a slope. Do we use the type of rover that we have now, a lot cleaner, or do we need a new kind of climbing capability? So there's a lot of basic research going on, but there's not a mission per se that's coming together for a special region.